Okay, and we are good. Questions on homework 1.1?
Jude, 24.
Okay, what does that say?
21.
It's a lot.
21.
Suppose a certain diet calls for 7 units of fat, 9 units of protein, and 16 units of carbs. Suppose that an individual has 3 possible foods to choose from to meet these requirements. Food 1 has 2 ounces of fat, 2 protein, 4 carbs. Food 2 has 3 ounces of fat, 1 ounce of protein, 2 ounces of carbs. Food 3 has 1 ounce of fat, 3 ounces of protein, 5 ounces of carbs. And I guess you want to just describe this with a linear set of equations.
Yeah.
Did they tell you what x, y, and z are?
Well, we assume of fat, protein, and carbs.
Number of ounces.
X is what? How did they describe it?
X, Y, and Z denote the
How many
number of
ounces
ounces
of
of
each
first,
food
second, and third.
to make the
Okay,
diet
all right,
requirement?
so, yeah, so x equals ounces of food 1, and y equal ounces of food 2, z equal ounces of food 3. Okay, so I know in total, right, so now I'm going to figure out how much fat do I want and how much I get. So for example, if I eat X ounces of food 1, how many ounces of fat do I get?
2.
Hmm?
2 ounces of fat.
If I look at fat, I eat X ounces of food 1. X, right? Fat from food 1 would be 2x. It's 2 times whatever, how many ounces you eat, right? If you eat half an ounce, you'll get 1 ounce of fat, and so on and so forth. The numbers here, they're telling you the proportions, right? So based on how much you're eating, right? So food 2, the amount of fat you get from that would be what?
2x.
3y, not 3x, right? Y is the number of food 2 that you eat, and so on and so forth. And then for food 3, you would have, food 3 gives 1 ounce of fat. So if you eat Z ounces of food 3, you actually get Z ounces of fat right away. So that's just Z. Now you want the total fat should be 7. Right? So this actually gives you an equation, and that's just for fat, right? So you have 2x plus 3y plus z equals 7, and that's one equation. You do the same thing for the other nutrients, proteins and carbs. You set it up in basically the same way. And so basically, the x column is determined by food 2, so you can really read those off. Food 2 gives 2 fats, 2 proteins, and 4 carbs. That's what you're getting from X. Food 2 has 3 fats, 1 protein, and 2 carbs. Right? So I go by fat, protein, carbs, right? Each equation is for one of those nutrients. And the X, Y, Z is food 1, food 2, food 3. Similarly, food 1 has
Z.
1.
yeah, we're looking at food 3. So it's 1
3.
ounce of fat, 3 ounces of protein,
5.
and 5 ounces of carbs. I need 7 ounces of fat total. I need 9 ounces of protein total, and I need 60. So that would be the set of your equations. And if you solve that for x, y, and z, that will tell you how many of each food you should eat. So it's kind of a long problem to work through, but when you start to break it down like that, it's manageable. Any other questions?
21.
Yes, one.
What does that say?
Prepare y equals ax squared plus bx plus c, shown in the accompanying figure, passes through the points x1, y1, x2, y2, x3, y3. Show that the coefficients a, b, and c form a solution of the system of linear equations. Whose augmented matrix is.
Wow. Okay. Well, let's say they never told us. How would we find that system of that coefficient matrix anyway? Let's pretend they never told us. What would we do? You plug these points into the equations, right? We know these things are true. We know that when my x is x1, my y would be the value y1. So I know that y1 would be equal to ax1 squared plus bx1 plus c. I know that y2 would be ax2 squared plus bx2 plus c. I know that y3 would be ax3 squared plus bx3 plus c. Now if I look at my coefficients, right, try kind of flipping things on its head. Look at my coefficients as the variables I have to solve for, right? So now I'm thinking of the a, b, c as the variables. These x1s, y1s are actually constants, right? They're specific points. There would be coordinates, right? Could be 2, 3, 5, 7, doesn't matter. But the x1, y1, these guys are going to be the constants, right? My a, b, c's are the variables. And so I can make a coefficient matrix by just taking the matrix of their coefficients. So this would be coefficient matrix equals the coefficients of this guy, x1 squared, x2 squared, x3 squared, coefficients of this guy, x1, x2, x3. The coefficients of c is always 1, and the solution column, the answer column is given by y2 and y. So the coefficient matrix would be this, and if you augment the system, you would get that. But yeah, you just plug these guys into that equation. You get 3 other equations. Your a, b, c's, think of those as the variables. Your coefficients come from the x1s and y. So technically, this is the augmented matrix, not the coefficient matrix that I wrote down. The coefficient matrix would just be this. Other questions?
23.
What does that say? Is that another
Show
word
that
problem?
if the linear equation x1 plus kx2 is equal to c, and x1 plus lx2 is equal to c. So if they have the same solution sets, then the equations are identical. That is k equals L and c equals d.
Okay. So same solution set means what? Means the pair x1, x2, or you can think of that as a solution vector. x1, x2 solves both. Right, so you're thinking of this x1 is the same as that x1, this x2 is the same as that x2. What I can do is just actually try to solve it. From equation 1, I can say my x1 is equal to c minus kx2. Plug this in 2, then this becomes c minus kx2 plus lx2 equals d. I can rearrange this, I guess, c minus d plus L minus K x2 equals 0. And then equate coefficients of both sides. Right? Which means that the coefficient of x2 on this side must be equal to the coefficient of x2 on that side. And so I know that L minus K must be equal to 0. Same thing, the constant term on this side must be the constant term on that side, which is also 0. So C minus D equals 0, which gives you the desired conclusion. Your L must be equal to K, and your C must be equal to D. Right, so if the x's are the same, their coefficients have to be the same.
Could
Could
you use another method of like when we cancel out equations, like finding?
Yeah.
Okay.
At some point, you should be able to deduce this one. Right. I used the substitution method. Using the elimination method would kind of bring them to the same conclusion. Other questions? What was that?
Suppose you are asked to find 3 real numbers such that the sum of the numbers is 12, the sum of 2 times the first plus
3 real numbers,
yes.
x, y, z, and the sum of them is what?
12.
So yeah, x plus y plus z equals 12.
Oh wait, never mind, I just, like, my brain totally blanked by the time I got this one.
Oh, okay.
But then the last part, that x3, they said like the second one, if you want to continue.
Okay, so we have 3 numbers, the sum is 12.
And then the second one is the sum of 2 times the first
2 times the first.
plus the second plus 2 times the third is 5. And then the third is 1 more than the first. So you just say x3 is...
Z is 1 more than the first.
So that's it, right? Okay.
So then you would write
In terms of like...
minus x plus z equals 1. Right? That would mean z is 1 more than x. Yeah. Huh?
We go for 19.
Which row does it see is equal to x?
Yeah, what does it say?
So 19, find all values of k for which the given augmented matrix corresponds to a consistent linear system.
Okay.
19a is a 2 by 3 matrix.
Okay. What's the first row?
First row is 1k minus 4, 4, 8, 2. 4, 8, 2.
4, 8.
2.
So we want to make sure k is such a value that this is consistent. Well, let's try to do a row operation on this and see what we can get. Let's say I want to kill this guy. What do I have?
Minus 4 or 1.
What can I do? Leave row 1, 1k minus 4, and let's do something like,
We can add minus 4 times plus
okay, I can say minus 4 row 1 plus row 2. That would give me what? 0. Minus 4 times this plus that gives me 8 minus 4k. Minus 4 times this is 16 plus that is 18. Now remember what we had for consistent, right? Inconsistent means you have a row that looks like 0, 0, and then a number at the end that's non-zero, right? In other words, if this is 0, that's bad, right? So 8 minus 4k not equals 0 for consistency. This means k not equal to 2, right? So consistent for all k not equal to 2. Yes?
Can you solve this question in terms of an intersection point value? Like for example, like I put these operation into system linear equations, And then I said to be able to solve for x for x2, we must multiply that first equation by 4 to be able to subtract the x1 is then solve for x2.
Yeah.
With that being said, that the K2 can act to 0 because that would mean the system would have no points of intersection. Can you do it like that?
You can think of it that way, because this last one you can think of as an equation. You're talking about like 1x plus ky equals minus 4 and 4x. Yeah, so this one would lead to the equation 8 minus 4k y equals 18. Now the only way you can solve for y is to divide by this, and then again, it being 0 would be a problem. You wouldn't be able to divide by it to solve.
I'm just saying, like, if that way it could work as fine, right?
Yeah, so you could say that and say this is only solvable for y if its coefficient is non-zero. If its coefficient is 0, it makes no sense. Can't do anything. Anyway, let's run along. Let's see if we can finish section 1.2. You guys sort of did it on your own already. I asked you to do it in the quiz. Put in what the two things we did together last time. So let's actually see it in action. So we're finally going to learn how to use row operations and augmented matrices to fully solve a system. And we're going to talk about all those cases that you can have. I wanted to start our discussion on determinants, but I don't think we'll have time for that now. So let's just do that. Get out of here. Okay, so we talked about the row echelon forms, and we talked about row operations. Let's actually put these guys to good use. So 1.2 continue. Let's talk about solving systems and the possible cases. Be doing this. Example: solve the following system: minus 2x1 plus x2 minus x3 equals 4, x1 plus 2x2 plus 3x3 equals 13, 3x1 plus x3 equals minus 1. The goal is to solve that system. Solving means solving for the x1, y1, x1, x2, and x3. So I can illustrate this with steps, I guess. Step 1, when faced with a problem like this, write the augmented matrix. In this case, what would that be? First row would be?
-2, 1, -1, 4.
Right, just look at the coefficients and write them down. So it's 1, 2, 3, 13, 3. Coefficient of x2 here is 0, 1, -1. That's the augmented matrix. That's your first step. Step 2. Find the reduce row echelon form or reduce row echelon form of this matrix. I'm going to illustrate finding the RREF. In general, it does not matter which one you go to. So if the question specifically asks you to find one over the other, just choose that one. Otherwise, personal preference. Okay? You will end up with the same solution either way. Which at some point I'll state that in a theorem or something. So let's actually do that. And while I'm doing this, I guess I'll state the kind of strategy that you want So let's see, the point is, here, you'd actually use row operations to do that. What are the row operations that we have at our disposal? What are the row operations?
Exchange.
You can exchange what?
The rows.
You can exchange any two rows, right? That's
Add. Like in multiplication.
multiply what? Multiply
Like for
what?
example, 2 multiplied by second row and
You
plus.
can multiply any row by a non-zero scalar. That's the second row operation. The third one is?
Addition.
What kind of addition?
To add the rows.
The third row is to replace a row by
Yeah.
itself plus a constant times
Yeah.
another row. This is called the type 3 row operation. You're going to do all those things in order to get this guy into a row echelon form or reducer echelon form. We're going to go for reducer echelon form here. And that's basically the idea. So you have to know what that form is. I gave you a list of specific properties that that form has last time. You need the first non-zero number in a row to be a 1. All these ones called pivots or leading ones, they must be strictly to the right of any one above them. Any rows of zeros must be all at the bottom. And in reducer echelon form, you must have zeros below each pivot and above each pivot, while in row echelon form, you only need zeros below. So that's the goal we're going to want to get. So now, let's find the most efficient way to do that. I will say this. The reducer echelon form of any augmented matrix, no matter what order you apply row operations in, it's unique. You can get to that answer by doing a multitude of things in a multitude of different ways, but you will get to the same answer at the end. This stands to reason. Some ways are more efficient than others, right? So you don't want to spend forever doing this, and you don't want to take too long. The thing is, at any given time, you're doing something really simple, but when you're doing a lot of simple things all at once, it's easy to make a mistake. Trust me. Like, even experienced people mess up with this simple arithmetic. It happens. So you want to be as efficient as possible, get to the answer as quick as possible, and just do things in a smart way. So we're going to talk about what that means in general. So in my time in learning linear algebra and practicing, I found that establishing the pivots first leads to a more efficient outcome. And you want to establish them quickly. So the first one is, I'm going to want to establish the highest pivot as soon as possible, then move on to the next pivot, then move on to the next pivot. That's going to be your main objective at any given time, right? So let's do that. My main pivot, I know it's a 3 by 3. I have numbers all over the place. It's going to be in the top left, right? My first objective, get a 1 in the top left in the easiest way possible. How do I do that? Switch 2 rows. Put row 2 on top. Okay, now, there are several options here. You can actually switch and copy down the other 2 rows, not doing a thing, and then wait another step to do another row operation. That's a waste of time. That causes more writing, more fatigue. Your brain is going to start getting tired really quick. You'll make a mistake. Immediately when you establish a pivot, kill everyone below it. Do not move on to the next step until there are zeros everywhere here. Okay? Efficiency. So once I put that 1 here, I'm not just going to copy rows. I'm going to start killing things in this column below that leading 1. Right? So how am I going to do that? Well, do another row operation right away. Right? So in one step, I'm doing several row operations. Right? So what I can do is I can multiply this by 2 and add it to that. So right away, I'm going to go 2 row 2 plus row 1. 2 times this plus that, it will give me a 0. 2 times this is 4 plus that, 5. Right? 2 times this is 6 plus that, 5. 2 times this, 26 plus that, 30. Right? Right?
Yeah.
I'm going to want a 0 here. Right? How am I going to get a 0?
Times negative 3 for the...
That's right. So I can take a minus 3 row 2 plus row 3. Right? So it's this minus 3 times that, 0. This minus 3 times that, minus 6. this minus 3 times that.
Negative 5. Is it?
So 3 is
Say
9.
negative
I confused myself about
Negative
Right.
Negative 8.
Negative 8. This minus 3 times that.
Negative 40.
So you see, in one step, I've established a pivot, killed everyone below it, right? No time wasting, right? The next goal is to establish the second pivot. I need that guy to be a 1, right? My first pivot is here. The next pivot must be to its right in a lower row. I'm going to aim to make that guy the next pivot, right? So once I get a 1 here, get a 1 there. Second objective. Recopy that. It is not my concern anymore. It's not a part of my objective, so I recopy row 1. My objective is to get a 1 here. What's the easiest way to get a 1 there? Divide by 5. Row 2 divided by 5. I will say this. If this was like a 7 and that was like a 9, I would not have done that. Right? Why? Because I get fractions. You guys were making mistakes when we had whole numbers. You see, it's easy to make a mistake here. You do not want to work with fractions. Sometimes, knowing that you could get a 1 here by just dividing, sometimes you let it go, right? You let him live for a while. I'm coming back for you. Don't think you're safe. I know, in my mind, you're really a 1. You think you're a 5, but I know you're a 1. I'm coming back for you. It's just not convenient for me to take you out right now, right? So if that happens, you just leave it, leave the 5 throughout the whole thing, and when you get to the last step and there's nothing else to do, divide by 5 and get fractions on the last step. Don't introduce fractions early. You will mess up, right? So the only reason why I decide to divide by 5 here and get that 1 right away is because everyone was divisible by 5. So I do that. Boom. Next thing, I want a 0 here. I'm not going to waste any time recopying down something. Okay? So I want those two to be zeros, which means I need to kill this guy. Now what am I going to do with that? I can take 6 times this and add it to that, right? So I'm going to take 6 times row 2 over 5, and I'm going to add it to row 3. Right? Remember, my rows refer to the previous matrix, right? So my row 2 here is referring to row 2 from the previous one. Row 3 here refers to row 3 from the previous one. So at the same time, row 2 over 5 is actually this line, so I'm going to multiply that line by 6 and add it to that. 6 minus 6 is 0. 6 added to this gives me minus 2. 6 times 6 is 36. Added to this, negative 4. That's my next line, right? Now, move over. Now, writing these guys here, these to actually list what row operations you're doing, it's not important to the process itself. It's kind of important for you. Like I said, sometimes their mistakes happen easily. You want to be able to look back at what you did and double check your work really quickly, right? So you don't want to actually redo everything you did and think through the whole process again. At any given time, if you feel like something's not working out here, you can just trace back. What happened to this row 3 above? This is what should have happened. Do all the numbers work out? It's like a roadmap for yourself. You can go back and you can check yourself what you're doing. So that's important. At this point, what can I do? This is a pivot. This is a pivot. Next objective, establish the next pivot, right? Establishing the pivots is the first step. That's easy. I can just divide by 2. So I'm going to take row 3 divided by minus 2. I would get a 0, 0, 1, 2. Okay. Now this guy, I already know he has a pivot here. This one I don't like though. I'm going for a reduced or echelon form, remember. So what am I going to do with that?
Substitution times negative 1 plus that one.
Right. So if I take
Negative row 3 over negative 2.
If I take row 3 divided by 2 and then add it to row 2, right? That's 0 plus 0, 0 plus 1, so it's 0, 1. I would take minus 1 plus 1, 0. I would take minus 2 plus 6, That's that row. Now the top one, there are two guys to kill, so I'm not going to expect to be able to do that in one shot, right? I'm going to take a couple, right? Each move I have to kill somebody though, right? So decide who we want to kill first. I can use this second row to kill the 2, and I can use the third row to kill the 3. Doesn't really matter. Let's kill the 2, just because. So that's going to be a 1. How am I going to kill that 2?
-2 times the second row plus the first row.
If I take -2 times this and add it to that, I have 0 and 1, okay? -2 times this plus that, 0. -2 times this is -5. -2 plus 3.
-1, just positive 1.
Come again?
Positive 1.
Then -2 times 6 is what?
12.
-12 plus 13. And what did I actually do? I took -2 times row what?
2.
Here. Move again. I'm going to want to kill that 1. That's actually easier to do, right? I'm just going to take this, subtract that row. 1 minus 0, 0 minus 0, 1 minus 1, 1 minus 2. And this is 0, 1, 0, 4, 0, 0, 1, 2. And this is row 1 minus row 3. Here I just copied this down. Row 2. This is in reduced row echelon form. Okay. Now that we have that, we can try to solve the system, right? How would we go about solving the system? Step 3. Are we step 3? Step 3. Starting from the bottom row up. Turn each row back into an equation to solve for the variables. I start from the bottom row up because we might have to back substitute in some cases, so we want to do that. So that's what I'm going to do. So from row 3 tells us that what?
x3 equals 2.
x3 equals 2 right away. Row 2 tells us
x2 equals 4.
x2 equals 4. Row 1 tells us
x1 is -1.
x1 is -1. In other words, the solution is x1, x2, x3 equals 2, 4, minus in the other order. -1, 4, 2. That is the solution to the system. This system had a unique solution. Does life always work out this nicely? No. Right? But do you see the idea? There's a strategy here. The point is you augment the thing, use row operations to get to the reducer echelon form or row echelon form, as is your preference or requirement. And then from the bottom row up, you turn everything back into equations. These equations will be a lot simpler to solve. And you might have to back substitute at some point. I'm going to show you some examples like that. And you can get to the solution. You just list it as a vector. You get the column vector. Some strategies to reduce the chances of mistakes or being too long-winded. First goal should be to establish your pivot, starting from the top one, going on down. Right? First thing, get a 1 here. Second second objective, get a 1 here. Third objective, get a 1 there. At any given time, once I get a 1, kill everyone below it. Because you can use that 1 and multiply by whatever you need to kill those other guys, right? So just do that all at once, right? Don't take like 3 steps to do this, right? You're gonna get tired. Keep adding it. Trust me, I've gone through this. Okay, establish this guy there, kill everyone below it. Establish this guy there, there's no one to kill below that guy, so that guy got away. So you have this, and then you start killing people above it. Once you actually follow this strategy, it's going to be easier to kill the people who are higher because there are zeros ahead of them that it won't affect the numbers on this side. It will only affect the number that you're trying to kill. That's why it's better to get the zeros below before above. It sets you up for, success, or whatever you want to call it, right? So that's sort of a strategy. The idea is augmented row operations get to reducer echelon form, read off the equations, you get the solution. Strategies, establish your pivots first, kill everyone below them next, kill everyone above them last if you want reducer echelon form. This would be okay as a row echelon form problem, but we went to reducer echelon form here. So let's actually talk about these aren't always this nice. In fact, this last step could be a lot sketchier than you think. Not a lot, but you just have to know what to do. In fact, there are 3 possibilities. There are only 3 possibilities. For any linear system. So there are 3 things you have to look out for, basically. Right? All linear systems, one of 3 things must be true in regards to solution. One case. The system has a unique solution, right? Which is what happened here. There's one vector that solves that system and only one vector, right? Only one vector will solve the system, so it has a solution. 2, the system has infinitely many solutions. That's another possibility. We'll do examples with that, right? So, for example, if you do something and you solve a system and you have 2 solutions, you did something wrong. You're either going to have 1 or infinitely many. You can't have 2, 3, 7. Not going to happen. Exactly 1 or infinitely many. Those are the only 2 ways a system can have a solution. The third is, of course, no solution. No solution. So those are the only 3 possibilities. I just gave an example that dealt with the first case, a system with unique solutions. Remember that in case 1 and case 2, the system is called consistent. Right? You can say the system is consistent and it has 1 solution. Or the system is consistent, it has infinitely many solutions. The last case where we have no solution, that's called inconsistent. And I'm going to do an example of each of these cases and show you how to deal with each. Any questions so far? Okay, so for any linear systems, one of 3 possibilities will be true. You have a unique solution, infinitely many solutions, or no solutions. In fact, I can probably illustrate this in. I can illustrate this in 2D, I guess. Those are the nice ones. Save myself from drawing planes, right? So there's the idea of the unique solution. Remember in quiz 1, what I did was I actually just solved a system, a 2 by 2 system, and it was and I asked you, what was the geometric interpretation of this? The geometric interpretation was, it's two lines and they intersected at a point, right? So I could have a line doing this, and a line doing that, and they'd only cross at one point. This gives you one solution to the system, right? There's a unique solution. You can't have two straight lines that are non-parallel, and they intersect at more than one point. It would mean you don't actually have a line, right? So it can have one point, right? So there's an example of that. You can have infinitely many solutions. Right? This basically happens when you have one line lying exactly on top of another. Right? Like you have the line y equals 3 minus x, and then you have 2y equals 6 minus 2x, right? They're really the same line. One is just a multiple of the other. Pretty much every point on one will be a solution for the other. This gives you an infinite many solutions. Then you could have the possibility where you have two parallel lines that don't intersect. Right? So I can have y is equal to 3 minus x and y is equal to 5 minus x, for example. Right? Those two lines will never intersect. They will never have a solution. And one of these three possibilities must happen. Right? So in 3D is a little trickier, and the more higher in dimension you go, it gets a little bit trickier. But that's basically the idea that's happening. Another example. Want to practice our raw operation technique. X1 minus 2x2 plus 3x3 equals minus 2 minus x1 plus x2 minus 2x3 equals 3 2x1 minus x2 plus 3x3 equals 1. X1 minus 2x2 plus 3x3 equals minus 2. Minus x1 plus x2 minus 2x3 equals 3. 2x1 minus x2 plus 3x3 equals 1. Solve that system.
Thank you.
If possible. First step.
Augmented matrix.
Okay, this is going to be what?
1 negative
1 minus 2, 3 minus 2, minus 1, 1, minus 2, 3, 2, minus 1, 3, 1. First step, establish the first pivot. This has already been done for us. Next step, kill everyone below it. I can just kill these two, recopy row 1, then add row 1 and row 2, right? Kill that guy. So 1 minus 2, 3 minus 2. Add these, 0. Add these, minus 1. Add these, 1. Add these, 1. Right? Then I can take minus 2 row 1 plus row 3. 2 minus 2. Minus 1 minus what?
2 minus plus 2.
It become plus 4, right? So what do I have? Huh?
4 plus.
I multiply this by a negative 2, which gives me a 4, positive 4. I add it to that. So plus 3. Multiply this by a negative 2, gives me minus 6. Add it to 3. And 3. Multiply this by a negative 2, which gives me positive 4. Add it to this. 5. Continuing. Second thing I'm going to want to do, establish this pivot. Not a big deal, just multiply through by negative 1. So let's do that. 1 minus 2, 3 minus 2. 0, 1, minus 1, minus 1. This is row 2 divided by minus 1. Now, I'm going to want to kill this. So what can I do here? I can just take 3 times row 2 plus row 3. So 0 plus 0, boom, minus 3 plus 3, 0, 3 minus 3, 0, this is 3 plus 5, 8. Now what do we do?
Stop.
Stop. Exactly. Why did you stop?
Because you don't have any x or y or z equaling.
0x1 plus 0x2 plus 0x3 equals 8. That means inconsistent. Right? Remember, this is something you're always looking out for. So this system actually has no solution. So basically, if you're thinking in 3D, like Calc 3, it means I have 3 planes that are parallel, but they never touch. Right? That's basically what happened here. I had like a plane going like this, and then there's another plane down here, and there's another plane down here. They never touch each other. That's kind of what happened. And it's possible for 2 of the planes to intersect. Like these 2 could really be combined into 1, but they never hit the 3rd. There's still no solution. That's sort of geometrically what's happening. So once you hit something like that, 0, 0, 0, 0, 0, something that's non-zero, inconsistent. I wanted to show you one with infinitely many solutions, how to deal with that, but I think we're out of time. So do that next time. I guess next week we'll there's not much to quiz you on Monday, so I'll try to just give you 1 or 2 problems to do. And we'll do that. Pass up your homework before leaving, and I will see you on Monday.